Can you both see that screen, that slide?
Yes, I can see it.
Yep.
Okay. All right. Well, I'll run through basically what we're going to look at today is bonding systems. So this is actually the third in a 5-part series, and we'll just look at bonding systems today. The next course in a month's time is on performance improvement for lagging and lagging and belt systems. We'll look at the most common forms of bonding used for pulley lagging, which is hot vulcanized bonding, direct bond, and cold bond. We'll have a look at how each of these systems work, the advantages and disadvantages. There isn't a perfect bonding system for every application, so they all have their advantages and disadvantages. And then we'll have a look at the adhesion testing for each system. If you've got any questions as we go, because there's only 3 of us, just interrupt me and I'll try and answer any questions you've got.
Okay.
So at Elastictech, we talk about what we call the 4 pillars of lagging performance, and that's basically lagging quality, lagging design, lagging application, and lagging selection. And you need all 4 of these to be working properly to get the best performance. Now, the bonding method for lagging is part of lagging selection. We'll also talk a bit today about lagging application, because obviously bonding and application go together. You can have a great bonding system, but if it's not put on properly, then you won't get the result that you're after. So we'll start off with direct bond ceramic lagging, as it's arguably the simplest and easiest to cover. The photo on the left is a drive pulley, and it's actually a combination of dimpled tiles and smooth tiles. You can see the dimpled tiles here in the center portion, smooth tiles on the edge. And the photo on the right is a non-drive pulley with smooth tiles. Now, there are 3 components for direct bond ceramic lagging. You have ceramic tiles, you have a 2-part epoxy adhesive, and you have a metal primer. The metal primer is there to protect the pulley shell from corrosion, because the lagging application process takes 4 to 5 days. And the adhesive is obviously what seals the surface of the pulley and provides the bond to the tiles. I'm going to show you, this is a time-lapse video, just to show you how direct bond ceramic lagging is applied to a pulley. It goes for a couple of minutes. You can see here the tiles are in pads, and what the operator here is doing is just measuring. So the tiles have been cut to fit the pulley face width. That tape has been put on just to mark the area that requires the glue. The glue is dispensed from a pneumatic gun. So the glue's in 2 parts, a part A and a part B. It's squirted through a nozzle, and it mixes in that nozzle. It's then trailed onto the surface so that you get a uniform coverage. And then the tile pads are put on top of the glue, and they're actually each individual tile is pressed into the glue so that it spreads out underneath the tiles. This is actually the next day, because that glue takes about 8 hours to go off. That's the reason we only do the top of the pulleys, because otherwise the glue and the pads would just slide off. So this is literally the next day. So the pulley's just been rotated, and now we're doing the next section, and it's a repeat of the process. The glue's put on with the pneumatic gun. It's trailed to get a uniform thickness. You can see there the tiles are being pushed into the glue.
Is it in your facility in Australia?
Yeah, this is in our factory, Glover. Yes.
Mm-hmm.
We don't actually do, like, this is not a service we do. We're actually, these pulleys, we were helping a customer out. We're not an application facility. We were just helping a customer out, and it gave us an opportunity to actually record the whole process.
Okay.
So they keep rotating the pulley. This whole process is over like roughly 4 to 5 days. You can see the ceramic is starting to come up on the bottom. We're nearly finished covering the whole of the pulley surface. So now we're at the last stage, and those bands of tiles that across the top, that's to actually measure what needs to fit into that gap. So we actually cut the pads to fit that gap. It's not a perfect fit, and you'll see what we do to make it a perfect fit is, now that we've got the tiles in there, you can see that they're pushing in these yellow spaces. So we actually cut the pads and we push these. They're like tile spacers you use when you're tiling your bathroom, and that allows us to adjust the gap in between the tiles so that when everything's finished, you can't even see the gaps. We're going to talk about adhesion testing today for each of the 3 different types. Adhesion testing is critical. It should be done on every single pulley to make sure that you get the right bond between the lagging and the pulley. For direct bond, we do what's called a shear adhesion test. This is the test procedure. You see there's a steel sample with a tile bonded on each side. There's a tile on each side. We're going to apply a load to the steel plate and measure the force that it takes to shear the tiles off. Okay, the adhesion force in this test was approximately 20 megapascals. Now the spec that's used in Australia for direct bond is a Rio Tinto spec, and they require a minimum of 15 megapascal shear force. Advantages and disadvantages of direct bond. Advantages: high bond strength. It's the highest of any of the different lagging bonding systems. Very stable bond strength for outdoor service. Direct bond pulleys can be in service for more than 10 years. The adhesive seals the pulley shell, prevents corrosion. You don't require any special equipment apart from the stands that you saw those pulleys on, and the process is very robust. The disadvantages of the direct bond is that because it's a rigid ceramic, it can damage the belt. It's got a long application time. That process you saw there was a 5-day process. If the pulleys are not designed properly and there's too much flexing in the shell, you can actually pop the tiles off. Direct bond on non-drive pulleys where they're contacting the dirty side of the belt can be a problem because you get build-up, and that can actually damage the belt, and it can also cause belt tracking problems. Because it is a rigid lagging, it's not kind to the belt or the splicers, particularly if you get material caught in between the belt and the lagging. It does require operators with a degree of skill, and it's very difficult to remove. So next, we'll have a look at hot vulcanized rubber-backed lagging. These photos, these 2 photos here, the pulley on the left, this is hot vulcanized ceramic lagging, and the photo on the right is hot vulcanized rubber lagging. The components for hot vulcanized lagging, you need the lagging strips, and they have an uncured bonding layer. This layer here is uncured rubber on the side and the back of the strips. You need a Chemlock adhesive, rubber cement, and a metal primer. This video will just show you hot vulcanized lagging being put on. So this is a pulley. It's been primed, treated. It's got rubber cement on it. And this is the process. So basically the strips, they have a plastic release liner that's removed. The back of the strips are sticky. So the strips put onto the surface and hammered down. So and in this case, because it's diamond lagging, we stitch all of the recesses between the diamonds to get good contact. And then all of the lagging is basically hit with a pneumatic hammer. This is just to make sure there's really good contact. Now, once the lagging's been put on, we then have to wrap it with a wet nylon tape. This is just a different pulley. This is a high tension gearless drive pulley. What they're doing here is they're applying a wet nylon tape. The tape's overlapped as it goes on. The reason that we put this tape on is that when the pulley is put into the autoclave and is heated, the water is driven off the tape shrinks, and that applies pressure to the lagging, which helps with the bonding. And this photo is the same pulley, and it's just to show you how we do the adhesion testing. So you can see these samples here. These are adhesion samples, and they're made using the same lagging that's been put on the pulley, the same bonding components, and applied to a piece of steel. And then they're wrapped. Because this is a very large pulley, we actually have 6 bond samples. We have 3 on each end, and they're spaced roughly at 120 degrees apart. This little graphic will just explain how the hot vulcanized bonding system works. So we have this gray layer here. This is a metal primer that's applied to the pulley. This green layer is a material called Chemlock, which is a bonding agent. We then have a layer of rubber cement, which is put on to make the pulley sticky, so we can get the strips to stick. Then we have our ceramic lagging. This grey layer here is a CN bonding layer that's built into the rubber. And then we have rubber cement, and the blue layer is an uncured layer of rubber that will react with the pulley. This will just show you how it all goes together. This is being put on, basically being put onto the pulley, and then we put this rubber silicon in the join. We put our nylon curing tape on the outside, and basically we cook it for 3 to 6 hours at 140 degrees C. And basically all of the joins disappear. There's a chemical reaction and everything combines. And basically there are no joins or weak points left. This is just another graphic just to show the curing process. So temperature goes up to around 140, 400 kilopascals of pressure. It's inside the autoclave for between 3 and 6 hours, depending on the size of the pulley. This graphic's just basically showing the same thing. The end result here is that all of the joins and separate pieces have combined into one, and this makes the whole lagging system very, very robust. One of the big advantages with hot vulcanized lagging is that there are no joins, so the pulley's completely sealed. You know, the water can't get to the shell and cause corrosion. This graphic I'll just show you. So this is basically what happens when a pulley goes around a revolution. Every time it contacts the belt, there's a stress applied. It's obviously a lot more on a drive pulley than on a non-drive, but the result is that there is a cyclic stress applied to the lagging and the joints. And in the case of hot vulcanized lagging, because there are no joints, there's no weak point there. This is just a side-on view. This is the end of a pulley. You can see this is where the join was. You can see it's all just basically one piece of rubber. And this picture on the right is a photo from the top of a join. You can see that there's no gaps. There's literally no way for any water to get through that joint and get to the pulley shell. So testing, very important that we do testing on the adhesion of hot vulcanized lagging. Basically, we do at least two test pieces for every pulley. So these are a bunch of pulleys that are about to be done. These are the pieces of steel. So they get prepared with the same bonding agents as the pulley. Very, very important. Sometimes in specifications, people will ask for adhesion tests to be done to ASTM or Australian standards or ISO standards or some other international test method. This is a completely useless exercise because the sample preparation and the method of producing the sample is completely different to what's going on the pulley. To understand what's actually happening on the pulley and be confident you've got the right bond, you must have the samples you're testing made from the same batch of materials as what has gone on the pulley, and they must be cured in the same way at the same time. Yeah, this is just a reiteration. Same lagging, same batch of adhesive, same application methods, and same curing conditions, and that gives you the best result in terms of knowing what's happened on the pulley. I'll just quickly show you the curing process. So this is basically putting the pulley into the autoclave. That's the autoclave behind. So it's basically a pressure vessel. The autoclave can be heated with steam or it can be heated with hot air. So the pulley with the adhesion samples is in the autoclave. We close the autoclave up. And then it's pressurized with air and with steam. Pulley that size will probably be cured for about 3 hours. A big pulley like the one you saw before, the gearless drive pulley, would be a 6-hour cure. Once the cure is finished, you obviously take the pulley out, remove the test pieces, and then the test pieces, we do what's called a 90-degree pull test. We basically measure the force to pull the lagging away. We're looking to see that the failure is due to rubber tear. And this is the sort of test result you get for a pulley. So on the left here, you want to have a record of what's happened in the autoclave. So you have time, you have the temperature and the pressure so that it's all logged. You know that something didn't go wrong in the middle of the cure. You know, the power went out, or, you know, we know that everything's been correct. Here you get the result at the top. We've got, in this case, 34 and 35 newtons per millimeter, and 100% MOF is motor failure, 100% rubber tear. So we're basically saying that the failure is just in the rubber. There's no debonding or delamination. The spec that we use for pass-fail criteria is the adhesion should be more than 20 newtons per millimeter, and the failure should always be 100% rubber tear.
David, do you do any additional tests on the ceramic tiles after to go to autoclave or something like that? This is just because, as I told you, we got this failure maybe 10, 12 years ago, and this make the client scared when these tiles start to leave the rubber. But the rubber in touch with the pulley, no problem. But the tiles, yes.
So debonding of ceramic tiles in lagging is a very common problem, and it basically it comes down to a couple of things, Glauber. A lot of manufacturers use the wrong bonding systems, and a lot of them don't have control. the way that they prepare the tiles. So it's an area that requires a lot of expertise. Also, what happens is when you put ceramic lagging into an autoclave, the temperature in the autoclave degrades ceramic to rubber bonds, so that the rubber bonds, the bond between the tile and the rubber drops off dramatically. Unless you design, you have to design the bonding system to be able to handle the hot vulcanizing process, and that's something that Elastic has done. So that this is a separate conversation that we can have. I can provide you with a lot of documentation and show your the client you're dealing with that problem has been solved by by Elastic. We can solve that, no problems.
Great, thank you.
Oh, sorry, I didn't talk about the advantages and disadvantages. Advantages: 100% rubber tear bond consistently. You can get hot vulcanized lagging lasting more than 10 years without any difficulty. It seals the pulley shell from corrosion. The process is very, very robust, and rubber-backed lagging is very kind to the belt and the splices because it's flexible. Disadvantages: you have to have an autoclave, that machine you saw there. If you don't have one of those, you can't put on hot vulcanized lagging. You can only put the lagging on in a factory. You can't do it when the pulley's installed on the conveyor. It does require skilled operators, and hot vulcanized lagging is very, very difficult to remove. We say if you want to avoid lagging application failures, always ask for adhesion tests on every pulley. It's surprising the number of pulley manufacturers that do not do any adhesion tests on their lagging, and they'll tell you they never have any problems, but if you don't test, you never know if you have a problem. Cold bond lagging. So this is the third type that we use. It's very, very common because it can be done on the conveyor or in a factory. It's applied at room temperature. So in Australia, that means typically between, say, 10 degrees centigrade and 40 degrees centigrade. In places where it gets a lot colder, if it's below 10 degrees C, usually you have to set up some sort of environmental protection and some heating to be able to do this. Cold bond lagging is made up of the rubber back strips, a two-part neoprene adhesive. So you have the adhesive and then you have a chemical hardener, and then you have a metal primer. This graphic shows the process. So basically you have your lagging here at the top. This black layer on the back is the what we call the CN bonding layer. It's a layer that's built into the lagging to help with adhesion. Here we have the pulley, metal primer on the top. I'm just going to, so this is, we coat the adhesive onto the lagging and then onto the pulley, and we bring the two together. And this, you can see this, I don't know if you can see this, these squiggly lines here. This is the interaction between the two layers of adhesive. They crystallize and they come together to form one layer. So just in a larger format, here's the ceramic lagging. This here is the CN layer that's built into the lagging. This is the coating of adhesive that's been put onto the back of the lagging and the sides of the lagging, and this is the coat of adhesive that's been put on the pulley. So important things to notice is this little area here. So there's an area on the side of the lagging where there's no bonding layer, and we have to put glue. This here is a weak point, and I'll show you why it's important in a minute. Basically, the whole process of putting cold bond lagging on is done at room temperature and room pressure. And for the adhesive to completely cross-link, it takes about 24 hours. Cold bond lagging is probably the most inconsistent of the three bonding methods, and there's a lot of variables. I'm not going to talk about all the variables, but one of the major ones, and Glauber, this we know is a problem in Brazil because of your tropical climate, but it's what we call the dew point. So when you put the adhesive onto the surface of the pulley or the surface of the lagging, it's a solvent-based adhesive, and as the solvent evaporates, it creates a cooling effect. And that cooling effect can cause moisture to condense out of the air and onto the surface of either the lagging or the pulley. And you can see this photo on the right. You can see this up here in the top. It's shiny. That's the adhesive. This bottom area where it's got a matte, cloudy sort of finish, that's actually moisture that has condensed out of the air onto the surface. It's sort of like when you have a shower and you get the fog on your mirror in the bathroom. That's basically what's happening here, and that layer of moisture greatly reduces the adhesion strength. To overcome this, we measure the dew point. The dew point is the point at which fog occurs in the air. So when you can visibly see moisture in the air. So we measure the dew point when we're putting cold bond lagging on, and we only want to be applying the adhesive if the temperature in the air and on the surface of the lagging is more than 5 degrees centigrade above the dew point. And this little table just shows you a difference of the adhesion strength you would get in a humid environment if you were to try and do the bonding close to the dew point, less than 5 degrees. It could be anywhere between 2 and 9 newtons per millimeter, which is very, very low. You could literally peel that. That means you could peel it off by hand. If you're above 5 degrees above the dew point, then you'd get more than 12 newtons per millimeter. Before I mentioned about this weak point, this is this point here between the lagging where this bonding layer doesn't exist up the sides. You've just got the adhesive. I'll just show you on this graphic. So again, cold bond lagging, just like hot vulcanized lagging, gets exposed to stresses as the lagging contacts the belt, goes around the arc of contact and then unloads. And basically what happens, you get an initiation of tearing up at the top here because it's the weakest point. The neoprene adhesive doesn't bond as well. Eventually, that will open up and give you a pathway all the way to the shell, the pulley shell. And then, of course, if there's moisture, if the conveyor is operating in wet conditions, it rains, etc., that moisture will find its way through that weak point and it'll come down to the shell. And what starts to happen then is you get corrosion of the surface of the shell, and eventually that corrosion will lead to debonding. Basically, the lagging starts to lift away from the shell, and the corrosion starts to eat into the pulley shell. These photos are just an example of how these joints can open up and result in debonding. This is another example, slightly different cause this time. And here you can see that the joints have opened up just in this central section. This is a result of, this picture here it's a pulley that's operating in contact with the dirty side of the belt. So it's operating with a worn belt profile. That worn belt profile creates localized shear forces. This is a graph across the belt width and measuring the minimum chord tensions inside the belt. So you get these peaks at the edge of the wear profile, and it's this cyclic localized shear that with cold bond lagging can cause this sort of separation and failure. So if we look at this photo on the left, this is a strip of cold bond lagging being removed from a pulley. The thing that I wanted to show in this photo is you can see here on the edge, this shell corrosion. This is what we call edge lifting or shell corrosion is very common with coal bond lagging because the edge is a weak point. This photo on the right is a hot vulcanized pulley. This is actually a pulley operating in Indonesia at PT Freeport, where they get 21 feet of rain a year, so it's extremely wet environment. The hot vulcanized bonding system is much stronger, and as a result, when you're dealing with wet conditions, it's less prone to having that sort of edge lifting. When you do get joints opening up, corrosion of the surface, this is commonly what you see when you're refurbishing a coal bond pulley. You get these lines of pitting. This is along the joins between the strips. One area where it can become a real problem is if the pitting in the shell is deep enough that you reduce the shell thickness below the design minimum, it means that the shell would need to be scrapped in those circumstances. Advantages and disadvantages. Coal bond lagging advantages, it's a very convenient system. In fact, it's the only system that can be used on the conveyor, and that's why it's very commonly used. It does provide a flexible bond, which is, with a rubber-backed lagging, it means it's kind to the belt and the splices. You don't require any special equipment for the application, and it's easier to remove than the other two types of lagging. The main disadvantage is that you do get very variable results. It's very dependent on climatic conditions. Often because people are putting it on the conveyor, it's dusty, dirty. It's very dependent on the operator's skill and expertise. There's a lot of things that can cause, you can get good results with coal bond, but you can also very easily get extremely poor results. It doesn't seal the pulley shell from corrosion. The joints are a weak point. It is important to have skilled operators putting it on to get the best results. It's not suitable for high tension applications. You would not use coal bond lagging on, for example, a gearless drive conveyor operating with high tensions, because the shear forces, the cyclic shear forces are too high for it. So this is just a quick summary of the three different lagging methods. You've got the direct bond ceramic lagging here, hot vulcanized coal bond. Adhesion strength, this is a comparison. The direct bond is by far and away the strongest, followed by hot vulcanized, and with coal bond having the lowest adhesion strength. Hot vulcanized does require an autoclave, so that restricts its use in a lot of cases. Robust application process, direct bond and hot vulcanized lagging would be considered to be robust. They both seal the pulley shell. Flexible bond, coal bond and hot vulcanized both provide a flexible bond which helps the belt. Yep. These are just some of the key requirements for consistent bonding. So you need to have detailed written procedures for the application of the lagging. You need trained applicators, clean conditions, adhesion testing on every pulley, and no shortcuts. These are just examples of the Elastic application procedures for each of those bonding systems. You can see here direct bond. This document, that's 32 pages. That's been developed over 10 years, more than 10 years. Hot vulcanized lagging is 35 pages. That's been developed over 12 years. Coal bond, 24 pages. So that there's a lot of detail that needs to be followed to actually get the best performance out of your bonding system. We do provide application training. It's a mixture of online training and also at site face-to-face training. This is all available from our website. If you go onto the website, you can see there's actually a list of people that are trained. And then over here, this section here, this is the actual training section where you can access the online courses. The course next month, so that's basically finished what I was going to say about bonding. The course next month, we are going to talk about identifying potential lagging and belt performance improvements. So we'll go through selecting the optimum lagging ceramic coverage. We'll look at challenges for drive pulleys and things that can be done to improve their performance. We'll look at challenges on non-drive pulleys, in particular high tension bend pulleys. We'll talk about spare pulleys and particular requirements they have. And then we'll also look at recommendations for different applications and different pulley positions. That's basically it from me. I don't know if anybody's got any questions.
No, perfect, Dave. Thank you so much. I'm really interested for this next course, next presentation. I'm going to motivate my colleagues from this conveyor group to join, because of course we are, as OEM, we depend of the pulley manufacturer on this, but we are interested to know more about this to really guarantee that our pulleys will have the high quality and will be confident on site. This is the point. Yeah, but I really appreciate that. I didn't know all these details. Thank you so much.
No problems, Glauber. And I'll what I'll do, you've given me, I think you've given me your email address.
Yes.
Okay. What I'll do is I'll connect you with Caroline.
Perfect.
Caroline's the lady that's visiting Brazil. She'd be a good one to talk to. She'll be able to help you with information on the bonding side of things, and she'll also give you access to a thing called Lagging Select. So Lagging Select is a software program that allows you to look at individual pulleys, and you put in the conveyor information. It'll tell you whether there's any localized slip. It'll tell you what sort of shear stresses are on there. You can compare different laggings. It's I think
I read about this. I see you guys have been developed this software together, Newcastle, yeah?
Yeah, so the university, the way this happened was we had a catastrophic lagging failure at the Cadia gold mine in New South Wales. They have a dual drive system. It's a 5 megawatt. It's their underground trunk conveyor, and it has two 2.5 megawatt drives. And they were doing an upgrade. They were changing from an ST 5600 belt to an ST 6300 because they were increasing the tonnage by about 15%. And they'd been running 25 mil rubber lagging on both pulleys for about more than 6 months with no problems. They changed the belt, and immediately on changing the belt, they started to damage the lagging. And within 4 weeks, the 25 mil rubber had gone to 15 mil. It had ripped all the diamonds off the lagging. So they had spare pulleys. They had to do an unplanned stop, which was 3 days, change the pulleys, and then we had to try and find out what was causing the problem. And they didn't want to go to ceramic lagging because they were worried if they made the lagging more abrasion resistant, they may have just transferred the problem onto the belt, and the belt was a 6-month lead time to get a new belt.
Yeah.
So anyway, we did a lot of work, and we worked with Conveyor Dynamics and also with Tamra.
Yeah.
You know the guys at Conveyor Dynamics?
Yes, Lawrence Nordell and his team. Yeah.
Yeah. So yeah, we worked with them, and that was the start of Lagging Select. We identified what was the problem. We put a new design of lagging on, which has been successful. And then we decided, well, maybe we can use this as a predictive tool.
Perfect. Sounds great. Yes, I used to say that these kind of bad experience, at least they increase our knowledge.
Yeah, you
Knowledge
don't
being
you,
the mistake. And
you
if we
don't
have
want the
this,
bad experience, but so long as you learn
uh,
from it, it's okay.
yeah, change the game, of
Mm.
course. Okay, David, it was a pleasure. Thank you
Thank you,
so much.
Glover.
Yeah,
All the best.
put me in touch with Kareem.
Bye
Take
bye.
care. Yeah,
Bye
see you
bye.
next round. Bye.